Hello everyone. Today we're going to talk about integrating exponential signals, and in particular complex exponential signals. We'll look at a few examples. This first page that I'm showing here shows you several formulas that you've seen before in your calculus class having to do with this function, this exponential function. Up at the top, you see we have here the derivative of the exponential function is the exponential function, and we can see that also the integral of the exponential is again the integral. But when we add an extra scale factor, we get a slightly different formula. This one can be derived using the chain rule, and then this integral formula over here using a change of variables. Very straightforward. If we have a definite integral with limits, as you see here, then we would end up with this type of a form. We have the exponential evaluated at the upper limit of integration minus the exponential function evaluated at the lower limit, e to the AU, all divided by the scale factor a. So let's put this function or this formula to use and integrate a few exponential functions of the type that we'll see in our signal processing class. So the first one that I'd like to do is the integral from minus b over 2 to b over 2 e to the j 2 pi f t df. The thing to notice here is that the interval that we're integrating over is a symmetric interval, so we're integrating from a negative b over 2 to positive b over 2. The total width of the interval is equal to b, and if we use the formula that we saw on the previous page, we would have e to the j 2 pi bt minus, that's b over 2, e to the minus j 2 pi b over 2t, all of that divided by j2 pi t. Now, I've written this in a way that hopefully suggests something to you. I'm sure you're familiar with this identity for the sine function. Sine of theta is e to the j theta minus e to the minus j theta divided by 2j. And if we compare that with with our integral over here, we see that we have e to the j something times e to the minus e to the minus j, that same thing, divided by 2j. And so that whole portion here, this turns into a sine. I'll write it like this: sine pi bt divided by pi t. When I wrote this down, I canceled the factors of 2 in the exponent, and so we just get sine pi bt. So if we're integrating a complex exponential over a symmetric interval, we get this sinc function. And one of the things that we need to be able to do very quickly given a sinc function is to make a sketch. Now, you know what the sine looks like. This is a sine that oscillates and has a period of 2 over b, and that function, that oscillating sine function, which is an odd function, we're also dividing that by another odd function, so the ratio here will be an even function. Odd divided by odd gives an even function, and it will look something like this. We know that the sine function crosses 0 whenever the argument is equal to a multiple of pi. So bt is equal to some integer k. That's going to occur at integers k over b. So if we line these up, here's 1 over b, 2 over b, 3 over b, and so on the t-axis. And then also we have negative 1 over b, negative 2 over b. And then if we were to sketch this in, it looks like a sine wave, sort of, with a decaying envelope. The decaying envelope comes from the 1 over t factor and so on. So it looks something like this. One of the things to note is that the total width of this region here that we're going to call the main lobe is 2b. And the other thing to notice is that the amplitude of this function at 0 is equal to b. And you can show that using L'Hopital's rule, or you can simply put t equals 0 back into the definition. When we do that, we'll have the integral from minus b over 2 to b over 2 of e to the j 0. That would just be 1 dt. And when you integrate that, you get b. So that gives us the amplitude right here at time t equals 0. Okay, so once again, in review, integrate a complex exponential over a symmetric interval. That gives us a sinc function, and we can make a quick sketch. We know where the zero crossings occur. We know what the amplitude at t equals 0 is, and so on. Okay, that's the first integral. Let's take a look at another integral here. Slightly more complicated, but not too much. Here we're going to integrate from 0 to t, e to the minus j 2 pi f t dt. So in this case, the change, there's two changes. One is that the interval that we're integrating over is no longer symmetric. It's this one-sided interval of width t. The other thing is that now in the exponent we have a negative. That's not going to really affect much, but let's go ahead and use the formula that we saw on the first page. So we can just write down the answer here. It's going to be e to the minus j 2 pi ft minus e to the j 2 pi f times 0. That would give us 1, divided by minus j 2 pi f. Now, what we'd like to do is use that sine formula to write this as a sinc function, but unfortunately in this case we don't have a symmetric form in our exponents in the numerator. And so what I'd like to do is teach you a trick that you can use to get that symmetric form. And essentially what we're going to do here, let's rewrite this 1 as e to the minus j 2 pi f times 0. What we're going to do, the trick that I'm going to teach you is this. We can get this into a symmetric exponential form, something that looks like a sinc function, by factoring out an exponential whose argument is the average of the arguments of these two exponentials. So if we take that average, we'll have minus 2 pi f, and then we'll have t plus 0 over 2. So that's the quantity that we're going to factor out. When we factor that out, what's going to be left is e to the minus j pi f t. Here I'll have e to the plus j pi f t. I'll write my minus j 2 pi f in the denominator, and then I'll multiply by e to the minus j pi f t. This is the exponential that was factored out, and we can check that this is correct by simply multiplying this factor back in. And notice what happens if we do. If we multiply e to the minus j pi f t by this term, we'll recover e to the minus j 2 pi f t. And again, if we multiply these two exponentials together, you can see that those will essentially cancel and we'll get back to 1. So by multiplying that back through, we can see that that is in fact equivalent. And now if we just play a few games with the negative signs here, I'm going to put a plus there, and a minus here. And now we can see that this part that I've circled here is equal to the sine function. So now we can just write this down as sine pi ft divided by pi f, and we have this complex exponential multiplying that sinc function. So there we have the final answer. And so this is typical. This is what you find if you integrate a complex exponential function over a non-symmetric interval. You'll end up with a sinc function times a complex exponential. Notice that in this example, the width of the sinc function was equal to the width of the interval was t, and we see t appearing explicitly in the sinc function. If we go back to the first example momentarily here, notice that the width of our interval was b to begin with, and we ended up with a b in our sinc function. And that's also typical. So we could use the same sorts of tricks here to make a quick sketch of this function. What makes the sketch here a little more complicated is that we have this complex exponential hanging out, which makes it inconvenient. But remember that the complex exponential is really cosine of pi ft minus j sine of pi ft. So we could use that Euler identity and separate things out. What's often done, though, is we know that this has a magnitude, this exponential function has a magnitude of 1. And often what we do is plot the magnitude as a function of frequency f. And in fact, I'll show you a picture of what that looks like here on the next page. So the top plot is a sketch of this function that we just derived. In fact, it's a little bit different. Let's see if we can make a slight adjustment to this without changing the actual function. I'm going to multiply by t and divide by t. And then what's being plotted on the next page is this alternative form, but you can see it's the same as the original function. There's two plots here. The one at the top is a linear amplitude plot, and the one here at the bottom is a log amplitude plot, log magnitude in decibels. So it's 20 log base 10 of the magnitude of the function. Here again, you can see that the zero crossings are going to occur whenever f is a multiple of 1 over t, and the amplitude of this function is equal to t, which is the scale factor out in front. All right. I would like to do one more integral. This one is will be the most general of the ones that we've seen, and incorporates the other two as special cases. But I think it's worth seeing this because it illustrates this trick that we've talked about for factoring out the exponents. So let's do this integral. I'm going to integrate from a to b of e to the plus or minus j 2 pi u v dv. So if we let u be frequency f and v be t, you know, this and use appropriate limits, we can recover the integrals that we've seen before. This one is going to be completely general, and we'll see that this type of an integral will encounter this sort of thing often enough that it's useful to have just a general identity. Okay, so if we write this down the way we've done others in the past using the formula, plus or minus j 2 pi u times b minus e to the plus or minus j 2 pi u a over plus or minus j 2 pi u. Now, I'd like to use this trick that we've talked about where we factor out the average of the exponents. So the average is going to be plus or minus j 2 pi u b plus a over 2. So we're going to have this exponential function here, 2 pi u b plus a over 2. That's the average. That's the part that we're going to factor out. And so what's left when we're done is going to be this, e to the plus or minus j, 2 pi u. We have b minus a over 2 minus e to the minus or plus j, 2 pi u, b minus a over 2. And on the bottom we have plus or minus j, 2 pi u. We probably should check to make sure that this is equivalent to what we began with. So the first term, if we look at the product of these two terms, we can see that here we have a b over 2 and another b over 2. So if we put those together, we'll get the 2 pi u b. If we look at what happens with the terms involving a, we have minus a over 2 here and plus a over 2 here. So those cancel, and we're just left with 2 pi u b in the exponent of the first term. If we multiply these together, we're going to be looking for cancellation because we wrote this as minus or plus, and this is plus or minus. And so notice this has a b over 2, this has a b over 2, but this one is minus or plus, where this one is plus or minus. And so the b's cancel out of this term. And this minus or plus times minus a over 2, that minus makes this a plus or minus on the a. So we get a over 2 plus a over 2, and we recover this other exponent over here. So I hope you can see that that's equivalent. And with that trick, we can write this down as sine 2. Well, actually, I guess I can cancel the u term, or the 2 in the exponent, because I have a 2 and a divide by 2. So this will just end up being pi u b minus a divided by pi u. And then we still have the exponential function. Pi u b plus a. And again, we had the cancellation over here in the exponent. You might be wondering, what about this minus j down in the denominator? And what that does is it fixes things up and changes the signs appropriately so that we get a sign function out of this when we use a negative sign in the original integral. Once again, we notice some things that we've seen before. One of those is that notice that the width of this interval that we're integrating over is b minus a. And you see the b minus a showing up here in the sinc function like we've seen before. If we were to sketch this out, the zero crossings would occur at, this is now the u-axis, this would occur at 1 over b minus a, 2 over b minus a, and so on. And we'd have a function that looks like a sinc function in between. So that's the general formula that we wanted to derive. I do expect that you can follow each of these steps, not just that you'll plug into this formula, or even that you'll really memorize this formula. I think it's if there's one thing to remember and to memorize here, that would be this trick, which involves factoring an exponential out with the appropriate argument. And remember that the argument that we're factoring out is the average of the arguments of the two exponentials that we started with. Okay. Now there's one other skill that I would like you to have, and that is the skill of making plots of these sinc functions in MATLAB. So let's talk about that for a moment. The question here is, how can we plot this sinc function in MATLAB? How do we plot this function? Well, MATLAB happens to have a built-in function called sinc, and it's given by this formula. And so if we want to plot our sync function, what we have to do is put it in the form of MATLAB sync function. Note that MATLAB sync function, the argument x appears in the numerator and denominator, and so we need to make our function look the same. So we'll introduce a t in the numerator and denominator, and the function that then we want to plot is t times sync of ft in MATLAB. Let's take a look at a little bit of code that can evaluate this function. Let's pay attention here mainly to the first 3 lines of code. Here I define a value for t, which is 1 second. I select an interval of frequencies over which I want to make a plot. Here I'm going from -5 hertz to +5 hertz in steps of 1/100th of a hertz. And then finally here on line 3, I'm using MATLAB's built-in sync function to evaluate. And all of the rest of this is plotting. The subplot command is used to make an array of 2 rows, 1 column, and this index is the first axis in that array of plots. And then we just say plot fs. I'd say give it a line width of 2 just so that it shows up a little bit better. Turn on the grid, label the axes, and then I go on and make the second subplot. This is again an array of 2, 1 column. This is now the second axis in that array of plots. And here I'm plotting 20 times log base 10 of the absolute value of the function. And I do the same sorts of things I did before. Here I'm setting the y limits so that it displays the informative part of the function, you might say. I'd encourage you to run each of these commands in sequence and see what they do so that you'll be able to repeat this sort of thing on your own. The last thing that I do is make a plot. So let's take a look and see what that plot looks like. You should see if you run all of these functions in MATLAB, you should see a figure window with these 2 axes, and you see on the top we have a linear amplitude plot, and at the bottom a log magnitude plot. With that as background, I'd like you to do the following. I'd like you to perform 3 integrals, do 3 integrations of the type we've done. Put your answers in the form of a sync function and then make linear and logarithmic plots in MATLAB. The difference between these 3 integrals are the intervals over which you're integrating. In the first case, it's a symmetric interval from -5 to 5. In the second case, you're going to have a non-symmetric interval from 0 to 10. And then here we have a union of 2 intervals, and so you'll get a couple of sync functions out of that. Notice here that in the instructions, I would like you to show all of your work, show the intermediate steps to get your answer into the form of these sync functions. Practice using that trick that I taught you of factoring out an exponential whose argument is the average of the arguments of the exponentials you get upon integration.